Hello my dear students, today we are going to discuss about the Solvay process, Plaster of Paris preparation properties and uses, beryllium chloride and aluminium chloride structure. Firstly, preparation of sodium carbonate by Solvay process. Sodium carbonate decahydrate is known as washing soda and its molecular formula is Na2CO3 10H2O. The anhydrous sodium carbonate Na2CO3 is known as soda ash. Do you know how the term soda ash originated? The name soda ash is based on the principal historical method of obtaining alkali, which was by using water to extract it from ashes. The word soda originally referred to certain plants that grow in salt marshes. It was discovered that the ashes of these plants yielded the useful alkali soda ash. Why is sodium carbonate called as washing soda? Carbonate from dissolved sodium carbonate can precipitate magnesium 2 plus and calcium 2 plus ions from hard water as the soluble carbonates, preventing them from forming a precipitate with soap resulting in scum. For this reason, sodium carbonate is also known as washing soda. Then what are the properties of sodium carbonate? Pure sodium carbonate is a white, odorless powder, hygroscopic. It means that it absorbs moisture from air. It has an alkaline taste and forms a strongly alkaline water solution. It is produced by Solvay process by using common salt, ammonia and limestone. This is the flow diagram for the Solvay process. It contains 4 towers: ammonia absorber, carbonation tower, lime kiln and ammonia recovery tower. The following 6 steps are involved in Solvay process. These are brine purification, ammoniation of brine, reactions in Solvay tower or carbonation tower, reactions in kiln or separation of solid sodium hydrogen carbonate, formation of sodium carbonate and ammonia recovery. Step 1. Brine purification. Brine or brine solution is a solution of salt or sodium chloride and water. Firstly, brine is concentrated by evaporation. Here, impurities such as calcium, magnesium and iron are removed by precipitation. Calcium ions react with the carbonate ion and to form calcium carbonate. Magnesium ion react with the hydroxyl ion and to form magnesium hydroxide. Fe3 plus ion react with the hydroxyl ion and to form ferric hydroxide. After removing the impurities, brine solution is then filtered and passed through an ammonium tower to dissolve ammonia. Through this process, energy is released because of its exothermic nature, thereby the ammonia tower will get cooled by this energy. In the Solvay process, second step is the ammoniation of brine solution in the ammonia absorber. Ammonia gas is absorbed in concentrated brine to give a solution containing both sodium chloride and ammonia. Step 3 is the reaction in kiln or separation of solid sodium hydrogen carbonate. Here, a lime kiln is used to produce quick lime through the calcination of limestone. This reaction takes place at 900 degrees Celsius. The heat of combustion raises the temperature of the kiln and the limestone decomposes, that is, calcium carbonate decomposes to give calcium oxide and carbon dioxide. The carbon dioxide sent to the carbonating or Solvay tower. The residue calcium oxide is used in ammonia recovery. Step 4 is the reaction in Solvay tower or carbonation tower. The Solvay tower is tall and contains a set of mushroom-shaped baffles to slow down and break up the liquid flow so that the carbon dioxide can be efficiently absorbed by the solution. Carbon dioxide on dissolving reacts with the dissolved ammonia and to form ammonium hydrogen carbonate. Then the sodium chloride react with the ammonium hydrogen carbonate and to give sodium hydrogen carbonate and ammonium chloride. Sodium hydrogen carbonate is the least soluble and it precipitates as a solid in the lower part of the tower, which is cooled. Step 5 is the formation of sodium carbonate. Here, suspended sodium hydrogen carbonate is removed from the carbonating tower and heated to 300 degrees Celsius to produce sodium carbonate. That is, When heating sodium hydrogen carbonate, it produces sodium carbonate plus water plus carbon dioxide. This carbon dioxide is passed to the carbonation tower for further reaction to produce sodium hydrogen carbonate. Step 6 is the ammonia recovery. Calcium oxide is formed as a byproduct of the thermal decomposition of limestone in the lime kiln. This calcium oxide enters a lime slaker to react with water and to form calcium hydroxide. The calcium hydroxide produced here is reacted with the ammonium chloride separated out of the carbonating tower by filtration. That is, calcium hydroxide plus 2 ammonium chloride gives calcium chloride plus 2 molecule of water plus 2 molecule of ammonia. This ammonia is passed to the ammonia absorber for further reaction to produce ammonium hydrogen carbonate. The next is the uses of sodium carbonate. The sodium carbonate is used as a water softener, food processing aid, pH modifier, swimming pool chemical and electrolyte. It is also used in the manufacture of glass, paper, paint, soaps and detergents and many other useful chemicals. It is also used in laundering and cleaning. It is also used as a laboratory reagent both in qualitative and quantitative analysis. This is all about the preparation of sodium carbonate or the Solvay process. Next we can move to another topic, Plaster of Paris. Plaster of Paris, a quick setting gypsum plaster consisting of a fine white powder, that is calcium sulfate hemihydrate, which hardens when moistened and allowed to dry. It is known since ancient times. Plaster of Paris is so called because of its preparation from the abundant gypsum found near Paris. The molecular formula of plaster of Paris is CaSO4 half H2O. That is, plaster of Paris is the calcium sulfate hemihydrate. Next is the preparation methods for plaster of Paris. Plaster of Paris is obtained when gypsum is heated to 120 degrees Celsius. When plaster of Paris is heated above 120 degrees Celsius, the water of crystallization is lost and the product is anhydrous calcium sulfate. It is called dead burnt plaster. Plaster of Paris possesses the remarkable property of setting with water followed by hardening. Plaster of Paris undergoes setting process by the formation of rhombic calcium sulfate dihydrate when treated with an adequate quantity of water. Subsequent hardening process involves the transformation to monoclinic calcium sulfate dihydrate. The slight increase in volume that occurs during the setting process causes the product to fill any mold completely, thereby producing an impression of the shape of the mold used. Plaster of Paris is used in the building industry. It is used in making blackboard chalk. It is also used in plasters used in surgery and for immobilizing fractured bones. Plaster of Paris is employed in dentistry for the diagnosis of orthodontic treatment, visual presentation of dental treatment, making of orthodontic appliances. It is also used in ornamental work and for making casts of statues, busts and toys. The next we can discuss about beryllium chloride structure. There are 3 different structures for beryllium chloride. In an isolated beryllium chloride molecule, it has a linear structure, the Cl beryllium chlorine bond angle being 180 degree due to sp hybridization. Such monomers of beryllium chloride exist above 900 degrees Celsius. In the vapor phase below 900 degrees Celsius, beryllium chloride tends to form a chloro-bridged dimer based on the state of sp2 hybridization for beryllium. The structure of beryllium chloride in the solid state is a polymeric chain. Here, beryllium atom is in a state of sp3 hybridization. So, the structure localized around each beryllium atom is an almost regular tetrahedron. These are the 3 different structures for beryllium chloride. The next topic is the structure of aluminium chloride. Aluminium chloride adopts 3 structures depending on the temperature and the state, that is solid, liquid or gas. Solid aluminium chloride is a sheet-like layered cubic close-packed layers. In this framework, the aluminum centers exhibit octahedral coordination geometry. When aluminium trichloride is in its melted state and in the vapor phase around 400 degrees Celsius, it exists as the dimer Al2Cl6 with tetracoordinate aluminium. This change in structures is related to the lower density of the liquid phase versus solid aluminium trichloride. Then, how the dimer of aluminium chloride is formed? Aluminium chloride is a covalent compound formed by sharing of electrons. The electronic configuration of aluminium atom is 1s2, 2s2, 2p6, 3s2, 3p1. The electronic configuration of chlorine atom is 1s2, 2s2, 2p6, 3s2, 3p5. Aluminium has 3 valence electrons and can form 3 bonds with the 3 chlorine atom. Hence, 3 bonds are formed by only 6 electrons, but it is not following octet rule. In aluminium chloride, aluminium has 6 electrons in the valence shell. Therefore, it is an electron deficient molecule and needs 2 more electrons to complete its octet. Chlorine, on the other hand, has 3 lone pairs of electrons. Therefore, to complete its octet, the central aluminium atom of one molecule accepts a lone pair of electrons from chlorine atom of the other molecule, forming a dimeric structure. Aluminium has one vacant orbital, thus aluminium can form one more bond. This bond will be a coordinate bond. Therefore, aluminium chloride always exists in a dimer form, 3 sigma bond and 1 coordinate bond per aluminium atom. Thus, octet rule is satisfied. Here, aluminium atom assumes sp3 hybridization. But at a higher temperature above 800 degrees Celsius, the aluminium chloride dimer dissociates into monomeric trigonal planar aluminium trichloride. Here, aluminium atom assumes sp2 hybridization. Today we have discussed about the Solvay process, Plaster of Paris, preparation, properties and uses, structure of aluminium chloride and beryllium chloride. I hope it will be helpful for you. Thank you.